Here's a sneaky screen classic, Ransom Note. It looks trivial, just letters, but interviewers use it to test whether you instantly reach for frequency counting instead of slow searches. Master this Pattern Mastery 100 problem and you'll crush dozens of "Can I build X from Y" problems in linear time. Let's knock it out with basic. Breakdown. We're given two strings, ransom note and magazine. We must return true if ransom note can be constructed by cut and pasting letters from magazine. Each magazine character can be used at most once, only lowercase letters. Assess. The right tool is frequency counts. Count letters in magazine, then scan ransom note and check we never request more than we have. With only lowercase letters, a 26-slot array is faster than a dict. Complexity, O(n plus m). Time, O1 space. Structure. Make an array CNT26 equals 0. For each char in magazine, CNT IDSC plus equals 1. For each char in ransom note decrement, if any goes negative, return false. If we finish, return true. Let's try to implement it using solution 1. We begin by defining a class called solution. This is where our method for checking if a ransom note can be built from a magazine will live. Here we define our method CanConstruct, which takes two strings. Ransom note, the letters we need. Magazine, the letters we are allowed to use. The method returns true if the ransom note can be assembled from characters in the magazine, and false otherwise. We create an integer array of size 26, one slot for each lowercase letter from A to Z. This array will keep track of how many times each letter appears in the magazine. Think of it like 26 little buckets, each bucket holding the count of a specific letter. This comment reminds us that the next step fills the buckets with available letters. This begins a loop over every character C in the magazine. We convert the magazine into a character array so we can process it one letter at a time. Since we scan the magazine once, this step takes OM time, where M is the length of magazine. We increase the count for the letter C. Here's how it works. A maps to index 0. B maps to index 1. C maps to index 2. And so on. So A gives us the correct bucket for this character, and we increment it. This comment tells us we're now going to use the counts we collected to verify the ransom note. This loop goes through every character C in the ransom note. We must ensure that each required letter is available in the magazine's character bucket. This loop runs in ON time, where N is the length of the ransom note. Here we decrement the count for the character C, meaning we're taking that letter from the magazine. If after decreasing it becomes negative, that means we needed more of this letter than the magazine provided. In that case, it's impossible to construct the ransom note. So if a letter runs out, we stop immediately and return false. If we finish checking all characters without encountering shortages, that means the magazine had all the letters needed, so we return true. And that's how this algorithm works. It first counts all available letters from the magazine, then checks whether each letter in the ransom note can be filled using those counts. Efficient, simple, and elegant. Solution 1. Test case 1. Let's test our function using this input. Ransom note equals A and magazine equals B. The ransom note tells us which characters we need, and the magazine tells us which characters we have available to use. In this case, the ransom note needs the character A. The magazine contains only the character B. Our frequency array counts what the magazine provides, and since A never appears in B, its count stays at 0. During the second loop, we try to use 1A, which decreases its count to -1, signaling that the magazine does not have enough letters to build the ransom note. So the function correctly returns false. And that's exactly what our program outputs, false. And this matches the expected result, false, confirming that our character counting logic works perfectly for this test case. So, our implementation is correct. The algorithm successfully verifies character availability using a clean frequency checking approach, efficient and accurate. Now let's try another implement approach using solution 2. Here we import Java's utility package so we can use helpful data structures like hashmap, which will store character counts for us. We define the solution class, which will contain our optimal, map-based method for solving the ransom note problem. This method, CanConstruct, takes two strings. Ransom note, the exact letters we need. Magazine, the pool of letters we're allowed to use. The method returns true only if the magazine has enough of each letter required to build the ransom note. We create a hashmap called countMap. Each character will map to the number of times it appears in the magazine, like a digital inventory of available letters. This loop iterates through every character C in the magazine. We're about to count how many times each character appears. This loop runs in OM time, where M is the length of the magazine. For each character, we check how many times it has been seen before using get or default C0. Then we add 1 and store it back in the map. It's just like updating the count for items in inventory. Every time we see a character, we increase its quantity. Now we process the ransom note, one character at a time. This loop runs in ON time, where N is the length of the ransom note. This condition checks whether the magazine has enough of character C. 2 failure cases. Exclamation mark count map dot contains key C. The magazine never had this letter. Count map dot get C equals 0. The magazine had this letter, but we've used them all up. If either is true, we cannot build the ransom note. In that case, we immediately return false, because we already know the ransom note is impossible to construct. If the letter is available, we use one copy by decreasing its count. This simulates taking one letter out of inventory. Since we reach the end without running out of characters, we return true, meaning the ransom note can be constructed. And that's how this algorithm works. It first builds a character inventory from the magazine, then checks and deducts characters needed for the ransom note, ensuring every requirement is met. Efficient, simple, and elegant. Solution 2. Test case 3. Let's test our function using this input. Ransom note equals AA and magazine equals OB. These strings represent what letters we need to form the ransom note and what letters we have available from the magazine. Here's why the solution works. The magazine OB contains 2 A characters and 1 B. The ransom note AA requires exactly 2 A characters. Our algorithm builds a frequency map of magazine characters. A2. B1. Checks each character in the ransom note. First A available, reduce count to 1. Second A available, reduce count to 0. Since we never run out of needed characters, the ransom note can be constructed successfully. And that's exactly what our program outputs. True. And the expected result is also true, confirming that our frequency map approach performs exactly as intended. So, our implementation is correct. The algorithm successfully checks character availability and ensures the ransom note can be built, efficient, accurate, and reliable. So, let's wrap up what we learned from this classic ransom note problem. It's a simple yet clever test of understanding how to use counts efficiently. Breakdown recap. We started by looking at what the task really means. We need to see if we can build one string entirely from another, using each letter only once. It's all about matching letter availability between the two. Assess recap. We compared possible approaches and realized that counting each letter's frequency was the cleanest way. Since we're dealing with lowercase letters, a fixed size array made it both fast and memory friendly. Structure recap. Our plan was simple. Count every letter in the magazine, then spend those counts as we check through the ransom note. If we ever need more letters than available, we stop right there. Otherwise, we're good. Implement recap. We put this logic into code, ran it on LeetCode, and the implementation worked without any errors. Check recap. After running multiple test cases, we confirmed that the logic holds up. Every check passed successfully. The key takeaway here is how powerful simple frequency counting can be. When faced with problems about matching or availability, thinking in terms of counts often leads straight to the most efficient solution.